Hello, everyone. My name is Yesha, and I came from the Department of Computer Science at Purdue University. Today, my talk is going to be solving satisfiability module counting for symbolic and statistical AI integration with provable guarantees. This is collaborative work with my students Jinzhao Li and Nan Jiang. So let me get started. The story actually starts from 2021, in which we actually show that automatic reasoning enables learning with provable guarantees. In particular, we work on Markov random fields models. This is one of the highly influential probabilistic models with a lot of applications in computer vision, natural language processing, bioinformatics, and so on. In fact, the original conditional random field paper received over 18,000 citations, and they are highly influential. However, the learning and the inference of MRF models are actually intractable. So here I'm showing you the maximal likelihood estimation for MRF models. As you can see, it involves computing this intractable partition function that needs to sum over an exponential many probabilistic scenarios, and this is computationally intractable. What we proposed was XOR CD, that actually is the first algorithm that converges in linear speed towards the global maximal likelihood estimation. Turning towards the second application, we also look at stochastic optimization. These are crucial problems for decision-making in uncertain environments with a lot of applications in operational research, econometrics, robotics, and so on. These problems also involves optimizing an intractable objective function that needs to sum over an exponential many probabilistic scenarios. And we again propose the first algorithm that has linear convergence rate towards the global optimal for convex stochastic optimization problems. We also look at leader-follower games. This is in the multi-agent optimization domain, in which you have the leader that commits strategies before followers. And these kind of games are also known as Stackelberg games and are the enabled theory behind many important applications in computational sustainability and AI for social impact. In particular, we look at quantum response games with exponential large action spaces. And again, we are the first to propose algorithms with provable optimization of quantum response leader-follower games with exponential large action spaces. So after working on these many different applicational domains, we asked the question, what do these problems have in common? And we find out that all these problems require a tight integration of symbolic and statistical AI. And in fact, this is one of the important research themes for next generation artificial intelligence. So for this paper, what we do is we generalize from specific applicational domains and to build satisfiability solvers that are able to reason about probabilities. So in particular, we add to set solver a module theory, probabilistic inference, and this leads to the so-called what we propose, satisfiability module counting problems as a tool for the integration of symbolic and statistical AI. In particular, SMC decides the choice of Boolean formula. These are symbolic AI that involves predicates whose values are determined by probabilistic inference. So this is the mathematical definition for a satisfiability module counting problem. As you can see that we try to find, these satisfiable assignments to a Boolean formula, phi of xb, in which a subset of these Boolean variables bi's, the truth values of bi's are determined by probabilistic inference. So these capture the statistical AI part. So for this paper, we consider a relaxed version of this SMC problem in which these bidirectional implications are replaced by this one-directional implication. We show that although this is a somewhat relaxed version of the SMC problem, it still captures many important problems in practice, and our algorithms are still widely applicable. So what we propose in this paper is this XOR SMC algorithm that has a constant approximation bound for solving SMC problems. What this XOR SMC algorithm does is it first transfer these SMC problems into a set problem. So as you can see that this phi star is a set formula, and then it calls a set solver to determine the satisfiability of this phi star, and based on the satisfiability, it returns either true or false. We show that this approach obtains a constant approximation bound, which means that suppose the original SMC formula has the solution when you tighten these probabilistic counting bounds by a constant multiplicative factor, then this XOR SMC algorithm will find that solution with high probability. On the other hand, suppose the original SMC formula does not have a solution. Even if you relax the bounds with the constant approximation bound, then our XOR SMC algorithm will determine that the SMC formula does not have a solution with high probability. Our XOR SMC algorithm utilizes an important connection between model counting and set solving with randomized XOR constraints. So let me illustrate this connection using this small example of counting the number of models for this small set formula. Okay, so in this application, we use 1 to mean true and 0 to mean false. So in this case, the sum of this big F actually counts the number of satisfying assignments or the number of models. So this is actually the two models of this formula, okay? But what makes it interesting is you examine whether these models satisfy these randomly sampled XOR constraints. So these are all the possible XOR constraints involving these two Boolean variables. So as you can see, there's an interesting fact that each of these model satisfies exactly half of these XOR constraints. This means that if you randomly sample one of these XOR constraints, then with 50% of the chance, exactly half the chance, your value assignment will satisfy this XOR constraint, and the other half it will violate it. Okay. Or put in another way, the number of models of this f of x conjunct with this randomly sampled XOR constraint is exactly, in expectation, is half of the number of models for this f of x. Okay. Now, why is this an interesting fact? Well, suppose you want to know if the model counts is larger than 2 to the 5, okay? So what you can do is you can determine this kind of set formula subject to randomized sampled XOR constraint. If you add one XOR constraint, as I'm presented in the previous slide, these actually filter out half of the the models. Okay, so and you can keep doing this, adding another XOR constraint, another one, and another one. Okay, so if the original model count is more than 2 to the 5, after you add 5 XOR constraints, you should still, with high probability, left with satisfying assignments. And therefore, this set formula of this f of y subject to 5 additional randomly sampled XOR constraints should still be satisfiable with high probability. On the other hand, if the model count is less than 2 to the 5, after you add 5 XOR constraints, this Boolean formula will have high probability to be unsatisfiable. Okay, now why is this an important fact? Well, consider if you are considering this SMC problem that has this intractable model count embedded in the original problem. Now, what you can do is you can substitute these model counting, predicates with this set formula subject to additional XOR constraints. And the satisfiability of this substitution will actually indicate very well the model counts. Okay, now because of that, this will transform this SMC problem into a set formula. Deciding the satisfiability of this set formula will solve the SMC problem with a provable constant approximation guarantee. In terms of experiments, we actually look at two applicational domains. One is in located emergency shelters, and these are important problems in integrating symbolic and statistical AI. And we find that our approach outperforms baselines, both in terms of running time and solution quality. And this also, is true for our second experiment of robust supply chain design. That is also an important application in symbolic and statistical AI. To conclude, the integration of symbolic and statistical AI remains an important research topic for developing next generation artificial intelligence tools. We propose Satisfiability Modulo Counting as one of the unified language to attack this kind of problem that is at the intersection of symbolic and statistical AI. We propose XOR SMC that transforms SMC into set formula with constant approximation guarantees and demonstrated superiority in two applicational domains. And this approach generalized to many other problems in AI, including in learning, stochastic optimization, solving games, and so on. Thank you, and I look forward to your feedback in the AAAI conference.